Welcome everyone. Today's webinar is entitled Consistency is Key, Best Practices for the F751 NIR Spectrometer. So today we're going to be talking about the 751. We'll be talking about methodologies that are currently being used. We'll talk about accuracy of the 751 and how we explain that, and talk about the different sources of variation that can arise when using the 751. 751 comes in obviously three different configurations right now. There's an avocado quality meter, a mango quality meter, and a kiwi quality meter. And these are each commodity specific. So today a lot of the data will be focused more on the avocado side of things, but the principles apply to across all of the 751 line. I also want to take this time to really thank anyone who's here from the produce industry. I know that things are really hectic for you guys right now. So really appreciate you guys taking the time to be here for this webinar. So let me first introduce to you our webinar host for today, Eric Munoz-Garcia. He is an application scientist. He's the other application scientist here at Felix Instruments. He's got a bachelor's in biohealth sciences from Oregon State University. He's got a lot of experience working in food analytical testing and dietary supplement testing, as well as DNA analysis, looking at things like identity testing and food fraud, FDA label compliance, things like that. So he's a great resource to have here and to have working with me at the Felix Instruments and CID Bioscience team. So if you haven't been on a webinar before, my name is Galen. I am an application scientist here at Felix Instruments. I have a bachelor's degree in biochemistry and a master's degree in food science from Michigan State University. I am an IFT certified food scientist, and I previously managed an analytical food testing laboratory and also worked as a food safety consultant in the produce sector, as well as the food manufacturing and cannabis sectors. So I'm really excited to be talking to you guys about the F751. So I've already kind of laid out a little bit of our agenda for today, but here's a little more specific look at what we're going to be talking about today. We'll start with the introductions, which we've already mostly gone through. Then we're going to go into the comparison of dry matter methodologies. So there's a lot of methodologies out there. We'll talk about those. Then I'm going to jump right into talking about our validation data that we provide for the 751 avocado quality meter, as well as the 751 kiwi fruit quality meter. And we'll talk about that data, and I'll explain the statistics that we used on those to do the analysis of that validation data. And if many of you, if you've looked before, this data is available on our website. And so I just wanted to kind of give you guys a clearer image of what the validation means. Then, in order to explain the sources of variance, how to increase your accuracy, how to compensate for any sort of biases in your instrument, we will go over just some of that information quick, and then we'll go into a case study and look at actual real data and I'll explain to you how exactly the bias or the offset correction is actually one of your most powerful tools to use in order to increase your precision and your accuracy. And then after that, we're going to go into our question and answer session, and both Eric and I will be available to help answer questions. And any questions that require a more in-depth solution, we are likely going to encourage you to go ahead and just email us directly so that we can address your specific problem more directly and more head-on. So let's start by talking about dry matter methodologies. So right now in the agricultural community, there is a lot of different methods out there for measuring dry matter. And these include, but are not limited to, oven drying through via forced air ovens, convection ovens, there's vacuum ovens, there's halogen lamp ovens, and then there's also dehydrators, which are kind of a similar take to the forced air oven, which are very commonly used. The microwave drying method, there's both manual methods and automatic methods. And then there is the freeze drying method. And also, lastly, what we're talking about today is NIR spectroscopy, which is what the F751 uses. So I think Eric has a poll for you guys, and actually we want to hear from you about what methodology you currently use to determine dry matter in your whatever commodities that you specialize in or that you test. So if you should see a poll on the screen here, and go ahead and answer whatever you use most commonly, and we will go ahead and look at the results of that and kind of talk about what we think about that. So I know that I know that, but you guys don't. But in our lab at the office, we actually try to employ as many of these different technologies as possible to see which one will give us the best results. And there's a lot of debate out there about removing moisture from food commodities, and so it's really hard to narrow this down to just which one of these is the most accurate, because as we'll see in a little bit with some data, they can oftentimes provide quite different results. But we'll go ahead and let you guys answer those poll questions. I know that a lot of you in the avocado community will likely answer microwave. I know that if you're in the kiwi fruit industry, you'll probably answer dehydrator, and oven drying likely for mango. Dehydrator also possible for mango. Usually the higher the Brix content or the sugar content in a fruit, the more difficult it is to utilize a microwave, because it lends itself to burning of the fruit more easily. So do we have results in yet, Eric?
So we have 67% of the polling complete. I'll give it 5 more seconds. Try to reach 70%. At 70%, I'll go ahead and end polling. If anyone is not interested in providing the information, then that's not necessary. This is optional, but I'll go ahead and stop the polling now.
All right. So what are our results here? All right. Okay. Honestly, I actually am a little bit surprised. I wasn't expecting, so you guys all should be able to see these results. The oven came in with the highest number of responses at 42%. The dehydrator coming in at 15%, microwave at 28%. What surprises me is the near infrared being 23%. That's really cool to see people embracing the new technology. And then 18% use another method, potentially something like freeze drying or another type of drying method. So yeah, the oven still is a tried and true method. It's one of the oldest methods that are out there. And a lot of people consider it to be, kind of this, the standard, since that's the way it's been done always. But as we'll see in a little bit here, there are differences between each method, and each method has its own inherent variability due to the fact that it is just extremely difficult to remove water from anything, especially a agricultural commodity, without removing non-water components or burning, combusting something on accident and causing a chemical change in the fruit itself or the vegetable or whatever it is that you are measuring. And so this is a quick little study we did in our lab. We happen to have these 3 technologies at our disposal. And so we just wanted to do a quick kind of anecdotal study about what we would get for differences in dry matter if we ran the same samples across 3 different dry matter methods. And so we did a classical dehydrator method, which was just a dehydrator at 60 degrees Celsius, for a minimum of 24 hours. And then we also happen to have, and we're testing this new technology from Sartorius. It's an automatic microwave. It's called the LMA 220. And so when I say automatic, I mean that you can program in different power levels at different time intervals, and there's a scale built in to the instrument. And so as the fruit or whatever commodity we're measuring, in this case it was avocados, as the avocado dries, it actually can detect the change in weight, and it'll detect when the fruit actually stops losing weight, essentially, from water. And once it's hit that endpoint, it'll automatically turn off the instrument and it'll spit out the value of dry matter for you. And you can see the dehydrator and that automatic microwave system from Sartorius were fairly similar. Then we also tried freeze drying or lyophilization. And with our freeze dryer, the data showed that our dry matter came out a little bit higher than with the dehydrator and the Sartorius. Now, the problem with running studies like this is that, yeah, it'll show us this variability. We really can't determine which one is actually right, which one's accurate, because there's just no way to know which one is actually getting out all of the moisture and not accidentally taking out non-water components. So, who's to say that the dehydrator or the Sartorius wasn't actually doing some combusting at that lower heat level and removing more volatiles or removing more, say oil, for example, than the freeze dryer was. So it's a really difficult thing to navigate these different methodologies. And I'll show you now some real data. This is not to say that our last study wasn't real data, but this is an actual study done by a third party. This is actually a data collected by our friend and collaborator, Dr. Jorge Asuna. He is with INIFAP in Mexico, and he was actually looking at the performance of the 751 across multiple different regions, different growing regions in Mexico, as well as looking at different sizes of avocado and how that affects the performance across these three different technologies that are commonly used in the avocado industry. So the 751 avocado meter, the oven drying method, and then the microwave method, which is most likely, and I think at this point now is the more popular method to use to determine dry matter content in avocados. And so you can see here that each method is providing a slightly different result. What the really key take home here is to look for the consistency in the method, right? So especially when you look at something like the caliber, the size of the fruit, you want it to be the method to be able to be consistent in across any sort of size of avocado. You don't want that to be another variable that's going to influence the readings of your method. So we can look and we can see that both the S751 and the microwave were extremely consistent in how they measured dry matter, across all different sizes of avocado. However, the oven, it seems, had quite a bit of struggle across the different sizes. And so this comes down to the fact that, every methodology is totally different, and it's not just the technology behind it, but it could also be your technique, the technique you're using for sampling the fruit, for, how you're, are you homogenizing it before you're putting it in the oven? There's a lot of different factors I can go into, like how consistent this method is. What we like about the 751 is that it takes a lot of those confounding variables out of the equation. There's no thinking about, how you are, are you using a desiccator to let it cool before you weigh it? Are you going to constant weight? Are you, what is your technique for actually sampling the fruit? And so the 751 helps eliminate a lot of those variables. And so it does allow it to be something that is less technique dependent, although there is technique still involved, and I will explain that later on. But it also, it's more of a consistency across analysts, across, different, users, as long as you're being, consistent in how you tell your users exactly how to use the instrument. And that's why the title of this is Consistency is Key, because really it is truly, even if you are talking about any other method out there, consistency is extremely important. Doing something the same way every time eliminates a lot of confounding variables that can actually really mess up and influence your data. So we talked about the methods. Let's just jump right into talking about some of our validation data. And so, as I already mentioned, this data we always post every time we come up with a new model. We always like to post our validation data onto our website for just full data transparency purposes. And so I'll take you through and run you through these, both for the data sets for both the kiwi fruit and the avocado, and then we will hopefully be able to give you a good idea of what metrics we used for evaluation and why we used them. So this table here, you can see just going through all the columns, we use two different varieties of fruit because that's what we built the model with, both Gold and Hayward kiwi fruit. The sample number refers to the fruit number. So this was 22 fruit in this study. We took the reference dry matter using the same method that Eurofins uses in order to do their dry matter studies on kiwi fruit by taking a slice out of the center of the fruit and using a dehydrator. And so these are the reference values. All this fruit came from a local market in Camas, Washington. So it was already fully mature fruit, which is another thing that I'll explain later on in this presentation as to why we do it the way we're currently doing it and how we are working to improve that process. But so we have the reference dry matter column, and then you have these groupings of 3 columns here in this data. And each grouping of 3 columns represents data from a single instrument. So when we validate, we don't just use one instrument. We use a wide number of instruments. In this case, I think we use 6, 5 or 6 different 751 instruments in order to make sure that the model is performing consistently, or at least to our standards, across all the instruments that are tested. And it's not just a fluke that it happens to work on one and it doesn't work on other ones for some reason. So you'll see that the number 19201, that is actually, when you look at the serial number on the back of the instrument, the format always goes 751 hyphen, and then there's a 3-number code, which represents the hardware version. And then after that, there's a hyphen, and then it'll give you a code like 19201. And that's the unique identifier for our products. And so each of those represents an instrument number. And in these 3 columns, we have the predicted dry matter, which is what the instrument told us was the dry matter for that fruit. And then we have the percent error of the dry matter. Now, when I say percent error, this is a relative measurement. So this error is actually going to fluctuate based on what the reference dry matter is. So the higher the value of the reference dry matter, then if you have, say, let's say, for example, 1% error. 1% error when you're measuring something that's 20% will give you a error of 0.2, right? And so if you were looking at 1% of something that is 1%, truly, if you're measuring something that is 1% and you're looking at 1% error, then you get down to extremely low levels of error. So the error actually level changes based on how large the number is for the reference value. And so this can be useful. It still can be a very useful measurement because it's a good goal to shoot for, right? It's a good goal to say, overall, no matter what your number is, no matter what value you're measuring, the error will always be less than this value. That's a good goal to shoot for. However, it's easier to put in terms of absolute error. And so when I talk about absolute error, that means that we're converting that percent error to a tangible number, and that number being dry matter percentage. So when we convert those to absolute errors, we can actually see how many dry matter units or percentages each measurement is off from the reference value. And so at the bottom, you'll see these average columns. And so the average is just showing that across all 22 of these fruit, when we are looking at the average relative error, the percent error, we're getting about 3.3% error. Now, 3.3% error for something that measures at 20% dry matter versus something that measures at 10% dry matter are two totally different things. And so what we're more interested in is the absolute error. So showing that on average, the instrument was reading 0.5% dry matter off from the reference dry matter. So the instrument, if you would take a scan and it read any typical scan on average, you'll take a scan. If it reads 18%, then our method will read 18.52. And that's on average. And then if you look at below that, you'll see two different error less than rows here. And so error less than 5%, this is going back to that relative error percentage. And so we were looking at how many of these samples did the 751 perform in a way that gave an error that was less than 5% relative error. And for the kiwi fruit model, for this sample set, it was 72.7% of the samples had less than 5% error. And then across the board, I think for all of these instruments, we never had a relative error that was greater than 10%. And so that's what it means when 100% of the error, 100% of the samples had an error that was less than 10%. So that's the kiwi fruit data explained. And now we'll go into the avocado data, which has a little bit more statistical metrics involved. And we will be, I am currently working on doing some reformatting to make it kind of easier to read for the average user. But this is a model validation study for the current avocado model, which is version 11. This was done in March of 2019 at our lab in Camas. And so this is looking at 29 different fruits, 29 different avocado. And with those 29 avocado, there was 4 scans taken from each avocado. And so when you look at skipping this top box really quick to go down to the actual data, you'll see a scan number and then a fruit number. So scan 1 is the first scan on the first fruit. Scan 4 is the 4th scan on the first fruit. And that's what the 1A, 1B, 1C, 1D designation is. So each fruit has 4 scans associated with it. This came out to a total of, due to the fact that we used 10 instruments for this validation study, this actually came out to a total of about 1,044 total scans across all instruments for all the fruit. And the average, so going back to the box here on the top, the average dry matter of the fruit was 31.63% dry matter. So that's taking the actual, which is the column down below, right after fruit. The actual is the reference method, a way of measuring. So with the reference method, We utilize dehydrator. And I think actually for this study, we did use the dehydrator as opposed to using the microwave. And so with the actual value, you take all of those fruit. So across all fruit, we average that value and we get 31.63% dry matter. Now, going back up to the top box, I already explained the reference method. It says dried and weighed. Obviously, that's a little vague, but for this one, I believe we did use the actual dehydrator. And then we have a reference method error of about 1.6%. And so that's just looking at the error, the average error between the values and then the average dry matter value. The results column I'll talk about in a second on this top box, but first let's go back down to the data. I know we're jumping back and forth here a little bit. This is why we will be trying to improve the flow of this validation data sheet. So what we want to look at is you can see the S and then the / and the N. That stands for serial number. So you'll see that as a shorthand notation for serial number. All of these numbers are associated with an individual instrument, a unique identifier for each instrument. And going down the column is the predicted value for that instrument for that scan of that particular part of the fruit. And so that's how we get all this data of what our error is and things of that nature, is by looking at comparing the predicted values, which are the values underneath the serial number column headers, and comparing that to the actual data, the actual being the reference values. And so going back up to our box here, looking at the results column, you'll see the first thing is this acronym RMSE. And so RMSE is the root mean square error. And we use this metric because it's a really commonly used, and it's a really good metric to use to investigate or to look at the typical standard deviation from the actual true value that a predicted value would have. So it's kind of like a take on error, but it's specifically used a lot in looking at model prediction and the robustness of model predictions. So calculating the root mean square error involves not much more math than taking an average error of something. Basically what you're doing is you're looking at the difference between the predicted value and the actual value. You square that, you divide it by the number of values, so the number of samples, and then from there you take the square root of that, and that gives you your RMSE. And so this is typically a lower RMSE it means that is a really robust model. That can be a little misleading because what is low? We don't. There's a lot of question is what low should look like, but an RMSE of 0.07 kind of indicates that that is the 0.07% dry matter is the average deviation based on the model's predictive ability. So that was a really good number to see. And then I already explained to you how the scans with error, the fruit with error less than 5%, but those are divided into two different categories because one is on a single scan, a scan by scan basis. That's the scans with error. And then the other one is fruit with error, which is groupings of 4 scans per fruit. So it's looking at the averaging those groupings of 4 fruit and then looking at the error based on the whole fruit itself. And so those numbers are there. And then the last is looking at average error per 1 fruit. So this is again per 4 scans of a single fruit. The average relative error was 0.14%. And then the average absolute error was 0.04 dry matter units, or dry matter percentages. And then we also just looked at the average error per lot of 5 fruit. So taking 5 fruit times 4 scans, that's 20 total scans. So increasing the scans from 4 scans to looking at 20 scans, our error went down, our relative error went down by 0.08%. And then our error, our absolute error, the dry matter units, went down by 50%. So it's now 0.02 as opposed to 0.04. And keep that in the back of your mind, because that's going to come into play later on when we're talking about sources of variance and how to mitigate variance within your instrument. So just know that when we are looking at the error based on 4 scans versus based on 20 scans, those metrics, the 20 scan metrics were essentially half of what the 4 scan metric was. So that's enough statistical talk, I think, for you guys for now. I don't think you were looking for a lecture on introductory statistics today. So let's start talking about the instrument itself, talk about the variance, all the different sources of variation, factors that affect the measurement variance, and then also I want to talk about how the offset, or what we call on the instrument the prediction correction intercept, is one of your most powerful tools to mitigate a lot of variability. So there are 3 sources of variance really within our instrument. We can kind of, we can funnel all of these different variations into kind of 3 sources. One of them, and one of the biggest confounding variables, is variation within the avocado itself. Avocado physiology creates a lot of variability within the fruit itself. And so things like measuring at the dorsal side versus the ventral, measuring the neck versus the body, measuring the outermost flesh versus the innermost flesh. All of those things influence the results of looking at dry matter. And we'll talk about that a little bit more in the next slide. The next one is variation due to the analytical procedure. So we already talked about this one at the beginning of the presentation. Each technique will provide a different reference or true value. And so it's really hard to determine which one is the actual correct, which one is the truest of all of them. But the key is to make sure that you are, doing things consistently, and also using instrumentation that is actually appropriate for the job. So, for oven drying, making sure that you're using, an oven that can hold a stable temperature and isn't going to fluctuate by, 10 to 20 degrees Celsius. So things of that nature, and consistent technique also being technique on the analyst's part. If you're going to let something cool before you weigh it after it just got done drying, you should be using a desiccator so that you aren't introducing new moisture into the fruit as it cools. Things of that nature. And then the third variation is variation due to the instrument. And this is where we'll get really in depth with it today. And that's where the case study will kind of come into. There's a couple different sources of variation from the instrument itself. And we'll talk about that variation from, the actual hardware, the electronics and the optics, and then variation from the model. And then variation from technique of using the instrument as well. So I said we would talk about more about technique, or not technique, sorry, about fruit physiology and why that's a source of variance within using the 751. And so there's lots of studies out there that have investigated the distribution of dry matter within avocado fruit. And now I'm focusing on avocado. I know there's a lot of you that are attending that might not be avocado growers or even care about avocado. A lot of other fruit have this issue as well. But I think that as far as providing sources of variation, avocado does a pretty good job of throwing in confounding variables as often as it can, just simply due to the nature of the fruit itself. So we're kind of focusing on the avocado right now, and so you can see there's multiple studies out there that showed that wildly varying distributions of dry matter within the fruit itself, based on its position, between the neck or the bottom of the fruit, the dorsal versus the ventral side, and then how close you get to the seed. The thickness, the closer you get to the seed, the less dry matter there seems to be. The farther out you are, there's more higher dry matter concentration. And so, with this much variation within a single fruit, it's really hard to get a full fruit idea of what the entire average of the fruit flesh dry matter is, unless you use a proper sampling technique. And that applies not just to drying it in an oven, drying it in a dehydrator, but it also applies to our F751 avocado quality meter, because our unit is not a single scan device. When it takes a scan, it's taking essentially what you can imagine as kind of a core sampling of that fruit. And so that would be like saying, if you were doing a destructive sampling, if you took a single core from a site on the avocado and you said, this small core represents the entirety of the average dry matter of the flesh within this avocado. That's just simply not true. And so the same goes for scanning things with the F751. If you are really interested in the entirety, the whole picture, you want the best idea of the true dry matter value within that avocado, you need to take multiple sampling sites, or with the 751, it's multiple scans. You need to take scans in multiple locations. However, if it's really more important for you, if you're dealing more in high volumes of fruit, then the best practice would be to the best of your ability to find a location on the fruit that's going to give you the most representative value for the entirety of the fruit. And from the research, it appears that for the most part, you would want to scan at the equator of the fruit on the dorsal side. And ideally, you would do it both at the dorsal and the ventral. 2 scans doesn't take that much longer than 1 scan. It's still just a matter of seconds. And so you would get the equator seems to be a good place to scan. Now, a little bit of a wrench in that. Thanks to Dr. Asuna, who I showed you his data earlier about the method comparison. He's also looking at the variation when you look at different sizes of avocado, and so it actually turns out that there can potentially be interference from the seed if you're using an avocado that has too thin of flesh, then you are likely going to encounter some sort of interference due to the nature of NIR technology. Our instrument penetrates far enough into the flesh that if your thickness of flesh between the seed and the equator is not thick enough, then you're going to get some interferences, and that's a new source of variability. So he will be likely publishing data later on this year, I think, in order to kind of look at what the best practice might be for avocados of varying sizes. And in the case where the seed is too large and interfering with the scans, measuring at the neck actually turned out to be a better practice. So just keep that in mind. Just keep in mind all the factors that can play in. Once you understand the technology itself and you understand what it does, it is a small aperture on an instrument that shoots light up into a fruit. it doesn't then take an entire image. It just takes, as you can imagine, just like a core sampling essentially of that location and give you a prediction for the dry matter of that location. Now, if it's trying to penetrate and it hits something like a solid seed or some other kind of solid object, that is going to cause some interference in the reading. And so with other commodities that have, say, lots and lots of smaller seeds, so kiwi fruit, for example, a lot of that is actually mitigated just by building the model correctly. And so if you're incorporating, those kind of, fruit that have high, seed count in your model, then it'll, the instrument will know, the model will know that how to predict just based on that. And so just keep that in mind. The fruit physiology plays a really big role in how the instrument works. And so, typically we do recommend if you are limited to 1 or 2 scans of the fruit, scan at the equator. However, keep in mind this whole new kind of emerging idea of the seed being a possible cause of interference. So I just kind of talked about, numbers of scans there. And so this is a good transition to look at these 3 different kind of use cases that will help you get an idea of what we mean by taking the appropriate number of scans. And so there's really, there's a few different options here. And so if you're looking at a single fruit, if you're trying to judge a single fruit, say you're a breeder and you really have a limited number of fruit to work with, and you need to know a single fruit's dry matter and you need to know it as accurately as possible. Well, in that case, it makes a lot of sense to take 4 or 8 or even more scans, as many scans as you can, to kind of get a whole picture idea of the fruit, because you want to know what the average is across that entire fruit. But if you're a grower and you're looking to look at the track harvest maturity in your plot, then you can simply take 2 scans of a few fruit from multiple areas within your plot, and so that would give you a good idea of the average across your plot. Really, it comes down to how big is your plot, and it's up to you to decide what the actual sampling pattern should look like. Typically, sampling fruit that is both inside the canopy, as well as all of the fruit that are kind of more edging towards the outside, will give you a good indication of the average dry matter for that plot. And then there's another use case, which is even higher volume, looking at packaging, packagers, people that are storage facilities, distributors, even like importers and exporters. Here you're going to be getting, truckloads and crates upon crates of avocado. And in order to assess the average dry matter of a group of those, you'll need, oftentimes we recommend, sampling at least 30 fruit, because with 30 fruit, you can tolerate having 1 fruit being out of compliance. But if you get 2 fruit that are out of compliance from your specs, then the fruit would fail. Then the whole batch would fail. So it gives you a little bit of that wiggle room. But taking, at least, 2 measurements per fruit is always the best idea. And ideally taking more if you really want the most accurate picture for the fruit. And I believe, Eric, do we have another poll question coming up here? I wonder if he's still on. Oh, there we go. So here's just a question for you, since we're talking about, these different use cases. The question is, how many fruit do you typically measure over the course of a season? So you should see the poll on your screen. If you would like to answer, I encourage you to do so. Just kind of helps us get an idea for, who you guys are and what's, what is important to you and what might be the better strategy. And so really the kind of take home message for talking about these different use cases is you can see all of them kind of equal out to a very similar number of measurements, despite the fact that you're either looking at, 4 fruit and that's all you have to work with, or if you're looking at 4,000 fruit, really it comes down to if you want that accurate number, you're going to have a pretty similar number of scans across the board, and it's not going to be one. You're going to want to take multiple scans, multiple sampling sites to get that most accurate value. There's other applications out there for this, I know, and everyone's specific application is going to be a lot different. If you are someone that is interested or is already a user and you have a really unique kind of situation, I highly encourage you to email either myself or Eric, and we would love to hear about what you do. So here are the results for how many fruit do you typically measure over the course of a season. And so it looks like the most popular answer being about 21 to 100 fruit, and then coming up pretty close is the larger facilities that are doing 1,000 plus measurements over the course of a season. So pretty interesting, actually. You guys seem overall pretty fairly evenly distributed, even when we talked about the methodologies, and now nobody coming in with a super commanding lead. So it's nice to see that we have a very diverse audience in here. Very cool. So yeah, the people that are doing the 21 to 100 measurements per season, for the most part, if you have that few fruit to scan, it is imperative to do multiple scans per fruit so that you can ensure that you're getting the most accurate results you can get. So I told you I'd talk about, lastly, the instrument variation and the different sources of that. And so let me preface this by saying that there is going to be variation in prediction value based on a single location with a multiple scan. So if you have one device, you put a fruit on it, you click the button, you wait a little bit, you click the button again without moving the fruit, there is going to be some variance in the prediction value. And then also you will get prediction value variance if you have 2 instruments lined up, the same fruit, you scan it on the first instrument and then in the same spot you scan it on the second instrument. Those 2 instruments are going to have variation between them. And so there's a lot of reasons why. And our engineers, when designing this, we've taken a lot of steps to make sure that that we are as consistent as possible on the hardware side of things. So compensating for external light leakage, measuring internal electrical noise and monitoring that, and then compensating for temperature changes within the instrument and things of that nature. So the hardware itself, we really work to make sure that it is providing as minimal variance as possible, because there are so many other external factors that can contribute. It's just imperative that we create the instrument to not increase the variance in any way due to the hardware or anything like that. So let's talk about the variation between the instruments first. When I was talking about the example, when you're looking at 2 instruments, the same fruit in the same spot, and the reason they don't might read differently. And so our current practice, and this actually also goes back to our validation data a little bit too, is that we calibrate each new production batch using local fruit from our local markets. And so we have taken this approach initially because we wanted to actually make sure that our models and our instruments are calibrated to actual fruit. And we thought that would be best. And so we, each production batch gets a new set of fruit from a different, potentially from a different region, potentially from a different season, one that's been in storage for a long time versus one that isn't. This one happens to be more ripe than the other one. So there's a lot, as you can see, there actually is quite a bit of variation between the batches of instruments. And so we've come to realize now that despite the fact that we initially thought that testing on fruit itself would be better for making sure that the model is predicting well, we actually are shifting our focus to developing a new process to eliminate that batch to batch variation and to ensure that all instruments going forward, regardless of when they were produced, when they were manufactured in our facility, will read as similarly as possible as a device from any other time in production. And so that hopefully will be a good method that will help eliminate or at least severely decrease that variation between instruments that you see. And actually, when I go into the case study, you'll see an example of how that variation between instruments plays out. And then the variation within a single instrument. So when you have a single device and you scan the same spot of the same fruit twice in a row and you get different values and you're wondering what's up with that, with each measurement, the built-in calibration model will interpret the attenuation of various wavelengths of light that have interacted with the fruit flesh. So there's a lot of things going on. And to be able to get the exact same spectra 2 times in a row from a fruit that's still physiologically, technically changing and ripening, it might not be at a very rapid pace, but there is change happening, chemical change happening within that fruit. Then that's what causes this variation within a single instrument. And so we'll talk about here in a second, but when you're seeing that, across fruit as well, and you're seeing that difference between what your typical methodology is versus what the 751 is reading, the offset or prediction correction intercept is a tool that's utilized to correct the predicted value if external factors are creating a bias in the measurements. And that's something I will go into more detail here in a second, don't you worry. And the next variation what we've already talked about here is from your sampling technique and the sampling size. So I just want to reiterate, the 751 is not intended to be a single scan device. It's not something that you can just put up to a piece of fruit, any fruit, click a button, and it'll tell you the complete average dry matter of the whole fruit, because that's just not how the technology works. It's taking a small sample from within that fruit and looking at that and predicting what the dry matter is of that small core sampling. And so by taking multiple scans of multiple fruit, utilizing the average of those, the user gains more confidence in the predicted value. And so I explained that as well in that validation data. So this is a callback to that validation data, the avocado validation data, where we are looking at the average error that was less than, or the average, average relative error and the average absolute error of 1 fruit versus 5 fruit. And we saw that when you're looking at the average error of 5 fruit, the error is decreased by by 0.08, which was over half of what the average error of 1 fruit was. And so in the terms of dry matter units, it went down from 0.04 dry matter of average absolute error for one fruit to 0.02% if you increase that number to 5 fruit. So, and remember, each fruit was 4 scans. So, so that's just something to keep in mind, is that if increased accuracy is what you want, the most powerful tool is to gain confidence in your predicted values is to take more scans in more locations on multiple fruit. And that will give you the better idea of the entire fruit's dry matter. So let's jump into this case study. I was talking a lot about prediction, correction, intercept, or what we also refer to as offset, a lot during this webinar. And so now I think is a good time to actually show you what that tool is and how it works. And so this is a good example. This is real data. Names have been eliminated in order to protect privacy. So this is data that was acquired. In this case study, it was 3 instruments that are from 3 separate regions of a country. And they were all compared against each other in the same laboratory and also compared against a reference method. So this is looking at not only accuracy compared to a reference method, but it's also looking at the variance between instruments. And so what this will demonstrate is how a simple offset correction can reduce both of those sources of variability. And so looking at these 2 graphs, let me just kind of lay them out here for you. The x-axis here is the reference method dry matter. The y-axis is the F751 dry matter. And so what we're looking at is for any given single data point, there is both a dry matter value from the reference method as well as from the 751. So it's comparing how those 2 match up. And ideally, you'll see there's a curve, there's a line built into both of these graphs. And that's looking at the ideal relationship, because if everything was ideal, then every scan of the 751 would predict the exact same value as the control or reference method. And that would result in them aligning in this straight line. However, that's not how it works in real life because of all the different sources of variance that we've talked about today. And so what you see here is on the top graph is a cluster of measurements that are in groupings by color. They're in groupings of one that is reading really well and on that ideal relationship line, one that's gathered kind of lower than the, and it's a little bit below the line, but it looks like it's trending in the same direction. And then we have another data set that's much lower than that, but also still trending in a similar direction as the ideal relationship. Now, if you apply the right offset correction for each of these data sets, for each of these instruments, if you look at the lower graph, this is what happens. You shift all of that data essentially upwards by a specified number of units. And that number is, as I'll show you in a little bit, is based on the difference, the average difference between your control and your 751 measurements. And so with this data shifted up, you now see all the data is now centered along the ideal relationship curve. And the data all looks much better. So another way to visualize this is to look at this type of graph. So some people prefer to look at this kind of graph when visualizing offsets versus what I just showed you. This is a simple line graph. The x-axis is the number of fruit, while the y-axis is the dry matter percentage value. And so the black line is the reference method. The solid lines are just the instrument data by itself. The dashed or dotted lines are the offset corrected data sets for both of the corresponding instruments. And so you can see, just like in the last graph, instrument 3, the green line, was already trending pretty well with the reference method, but instrument 1 was trending slightly lower, and instrument 2 trending notably a lot lower. And then once you do the correction, once you input the correct offset, that data now all goes back to being centered just around the reference method and predicting much more accurately. And now looking at the raw data itself, this is a good example at both showing you how we come up with the offset, but also showing you the power of increasing your number of scans or increasing the number of data points you have. And so you see this column titled deviation from control. That's just looking at the difference between what the instrument spat out as a predicted measurement versus the reference method. And so if you look at the first column of deviation from control, looking at instrument 1, so the first reading for instrument 1, for fruit number 1, it was reading 1.3% dry matter lower than the reference method. And then you go down the column and you see for each of these fruit, there's a deviation from the control. When you average that deviation, you actually get a good idea of how much of an offset you need to input into your device. So that value, that negative 3.1, once that negative 3.1 is put into the device itself, the model will then understand that all data that it spits out needs to be increased by 3.1% dry matter, because there is an inherent bias in the model's predictive ability. And so once it knows to do that, you can get your new predicted set of values, and you can see that even though we've now adjusted for the offset, you'll notice on a single fruit basis, there is still a deviation from the reference method with every measurement. And in some cases, you might see an increase, you might see a decrease in that deviation. In general, most values will decrease from the original deviation without the offset. Now, when you're looking at on an individual fruit basis, you're like, wow, some of these deviate, quite a bit, or more than I'm comfortable with. Yes, so that's the same reason why this is not a single scan device, because when you look at these individual fruit on an individual fruit basis, there is always deviation. However, if you look at the average row at the bottom, and you look at the average across all 10 of those fruit, the average of the reference method is 21.4% dry matter. The average of those 10 fruit for each of these instruments that were offset corrected is also 21.4% dry matter, which means that the more scans you take, the more fruit you incorporate, the higher your sample size, the more accurate this device is going to be for you. Sure, on an individual basis, you are seeing deviation. However, at the end of the day, when you go to average all of these, your offset, or your error percent just is extremely, extremely low. And in this case, it was 0. So that's just to show you the power of using the multiple scans, multiple fruits, in order to get the most accurate idea for your study or for your application. And so that's all I wanted to show you guys today. It's, there's a lot of statistics we could dive into. There's a lot, to talk about when it comes to model building and things of that nature, but this is just kind of to show you guys the best practices, tools that you can incorporate yourselves into your practice in order to help increase the accuracy for your use. And so just in summary, we talked about the dry matter methods. There's really no way to determine which one is the most true of all, but each method has its own inherent variability. And we've seen that both in anecdotal and real life data, that every method, is gonna predict slightly differently from one another. And the most important thing is to look for a method that can be as consistent as possible. We then talked about the validation data, and I talked about all the key statistics, how RMSE is used. We use that to look at the robustness of the model, to look at the typical standard deviation that a predicted measurement would have. And so also talked about sources of variance. So looking at the variability comes from one of the three sources, right? The physiology of the fruit, the instrument itself, and then the reference method that is being used to build and validate the model. And lastly, and one of the more important messages here to take home is that while we have taken lots of measures to minimize the variability from the instrument from a hardware perspective, there are just variables that we simply can't control. And in order to overcome a lot of this variability, all it takes is for the user to utilize the offset correction, also known as the prediction correction intercept. And it's really extremely powerful tool to help reduce the variability between instruments, variability within one instrument. And so, yeah, I think, Eric, do we have another poll question here before we get into the end of things?
Yeah, so we do have another poll question.
Let's go ahead and jump into that. So this is a question that we want to know, just to kind of get to know you guys better. It's just to kind of get an understanding of our audience, and we just want to know which part of the supply chain do you guys work in. So if you feel comfortable answering, we would really appreciate your feedback to get to know, who we're talking to, and who is interested in learning more about the 751. So yeah, so actually, we'll go ahead and advance to the next slide while we wait. But I really appreciate you guys all, taking the time out to be here. We'll be at the Q&A here in a little bit. Once this poll is over, I'll just have a little bit more to talk about, and then we'll jump right into some questions and answers. In the meantime, I hope everyone's staying safe and during this time. I really appreciate you guys being out here. So looks like the results are in. Again, fairly even distribution across people that are growers, packers, importers, exporters. And we have a few people, breeders. We have some retail folk here. And we have a whole heck of a lot of people that are other. And I think we probably should have put something like research or something like that in this poll, because I have a feeling that some of you might be in that category as well. But thank you for answering that poll. Before we end here, I just want to talk to you quick about a couple of our offerings. So we do have the F751 Kiwi quality meter is now for sale. We released that back in February. And it works for both dry matter and Brix measurements in gold and Hayward kiwi fruit. And then we also are really excited about our upcoming release. It's to be announced, but we are really excited about it. It's our new CI 710 SpectroView leaf spectrometer. And so it is another spectrometer offering we have that's more focused towards plant research, has lots of built-in indices for color compounds, carotenoids, chlorophyll, anthocyanins, things like the NDVI index are in there. And then also the 710 will have the ability to create PLS models similarly to our F750 produce quality meter. So if you've always wanted to build a model to measure water and spinach leaves or something like that, then this instrument will be a perfect fit for you. So to wrap up here, if you guys want to get connected with us, if you want to keep up with what we're doing, the best way is to visit our website. But also you can always follow us on social media, Twitter, Facebook, or on LinkedIn. You can email us if you have sales questions. You can always give us a call as well. And once this whole quarantine is over and things have returned to normal, if you happen to be in the area, you can always stop by our headquarters in Camas, Washington. We're right outside of Portland, Oregon, and we always love to have visitors. Not during this time. Please do not come visit us if you are thinking about it during this time. But once the COVID-19 pandemic has kind of tapered off, maybe then would be a good time if you happen to be in the area. We do love visitors, and we'd love to take you around our facility. So that's it for the presentation. We'll jump into the question and answer session here. If you do want to quote, go ahead and Eric will be posting a link in the chat, this tiny URL, Accurate Dry Matter, that will take you directly to our quote system. If you would like a consultation, so before we jump into these question and answers, if you have something that's a very specific to your situation, it requires more detail than I could possibly give you over a quick answer via webinar. If you have a question about how you can apply your technology to whatever operation you have, please go ahead and schedule a consultation. Eric and I are both more than happy to talk to you, help you figure out, how you can utilize our instrument, or help you go through your data, figure out, what's going on if you're having any sort of difficulties. So if it's something very specific to your operation or specific to your data kind of question, it's better off if you email us directly or set up a consultation. And in either way, we'll get back to you with that. So with that being said, I'm going to go ahead and open the question and answer box. So the first question is regarding and actually, you know what, I might end up in this having to kind of go back to some slides to reference them, but the question is, hi, explain why absolute error is much lower than the error in each row. So the absolute error is basically the percentage relative error multiplied by let me pull up the slide here. I wonder if we're talking about, let's do this one. Yes, okay. So if we're looking at this first column here, our percent error is a relative error. So that's saying that 18.59 is 5% off from 17.65. But if you look at just this number, 18.59 minus this number, it gives us the absolute error, which is 0.95% dry matter. So I think the confusion might be coming from the fact that dry matter happens to also be in a percentage value. We're talking about percentage of errors, and then we're talking about dry matter percent. So think of the dry matter percent as a dry matter unit. And then the percent error is the relative error. So even though 18.59 is 5% error-wise, it's 5% off from 17.65. If you look at it in strictly terms of dry matter units, 18.59 minus 17.65 is going to give you a 0.95 difference. Okay. And
before, I also wanted to mention that the webinar is recorded, and if you're in attendance, you'll receive an email to the link to the YouTube page, which will have the webinar.
Awesome.
And Galen will also be posting the presentation PowerPoint slides as well.
Yep. Awesome. Thank you, Eric. Yeah. If it was at too fast of a pace for you, or if it was something you want to show your colleagues or something like that, then if you have registered, yes, you will be receiving recordings. You'll be able to see the actual just PowerPoint itself, all of that. So So the next question is, what is the relationship between sugar content and dry matter of a produce? Does sugar content of a produce affect the dry matter using all methodologies? Thank you. Okay, so this is a two-parter question. The first part, the relationship between sugar and dry matter. So dry matter, even though it's technically, defined as anything that isn't water, right, within the fruit, for the most part, people look at dry matter as being correlated to the starch content of a fruit. And so as a fruit matures, it gains more starch content. And then as it ripens, it actually will start converting some of that starch into sugar. And so over time, after ripening, you'll have this kind of change in balance from dry matter, from starch turning into sugar. Where that plays into how it affects how does sugar content affect the dry matter using these dry matter methodologies. For the most part, what we've found in all of our studies is that the higher the sugar content of a fruit, the more difficult it is to use any sort of microwave method or kind of faster paced or higher temperature methods, because the sugar will start to burn more easily. The higher the sugar content, the easier or the more prone a fruit is or piece of produce is to being burned. Burning something obviously is a change in chemical composition, and it actually does influence, especially when you're doing something, a test that is a gravimetric test, which all of these tests are, except for all these methodologies are gravimetric besides the NIR method. When you're doing something gravimetrically, losing weight that isn't weight being lost by water loss will actually kind of artificially inflate or technically deflate your dry matter value. And so burning overall is something that happens across all methodologies if you do it wrong. Besides also, I suppose, freeze drying, which is not very commonly used technology for dry matter tests, but can be used. But for ovens, if you have too high of a temperature in your oven or on your dehydrator, and if you try to use a microwave, then you will likely burn your fruit, and it will give you a incorrect or inaccurate value for dry matter. So that is the question, that question. And then the next question is, if you scan a fruit again in your validation example, do you move the fruit off the F751 and place it back? And are you measuring on the same spot for the 4 measurements per fruit? Oh, okay. So this is probably referencing the avocado. If talking about 4 measurements, let me go to that slide. Okay, so to answer your question, we don't do 2 scans in the same spot. So if that was something that interested you and you wanted to scan the same spot in the fruit, there's multiple options there. So the best practices would either be to mark the precise location on the fruit where you scanned, and then you can remove it and then put the fruit back on, or you wait an appropriate amount of time before taking the second scan. Because what you're going to do if you just keep continuously taking scans back to back, that's a really powerful lamp, and you're actually altering the temperature of the fruit itself, which is another factor that plays into how the model predicts. And so you don't want to be taking multiple scans in a row like that. So if you are going to leave it on in the same spot and choose not to mark the fruit, then leave it on, but allow it time to kind of stay at room temperature so you aren't artificially heating the fruit. As far as were we measuring on the same spot for the 4 measurements per fruit? No. So how we do it is along the equator, we take 4 equidistant measurements. So we would take 1 on the dorsal side, 1 on the lateral side, and then 1 each on the other 2 sides. And so we have 4 scan sites around the equator of the fruit, 4 unique scan sites. And that also answers the next question, which is about the same question about the 4 scans. So yes, it was 4 different spots, equidistant along the equator of the fruit. The next question is, so is the F751 accurate to around 0.14%? The average error per 4 scans, so 4 scans to 1 fruit, the average relative error was 0.14%. And that is with our validation data. So this is fruit that was acquired from local markets, fruit that was already fully mature. And so for that purpose, yes, the error was 0.14%. Can we make a blanket statement and say that it's always going to be accurate at 0.14%? No, we cannot, because there are so many other variables that are going to come into play. But in the case of this data set, that's the accuracy we saw, and it is, you know, a good general predictor of saying, in general, you will see accuracy that's pretty similar to that. The next question is, can this 751 be used for other fruits, i.e. can we develop our own calibration? So actually, that's what we have the F750 for. The 750 is a research version of the 751 in which you can build calibrations for any sort of commodity you wish. And there, we actually have some webinars on. We have a webinar online, I believe, about the 750, and lots of more information. If you need more information on that, you can feel free to email us, and I can provide you more. But the 751 is strictly to be used with just the commodity that we name it, essentially. So whatever commodity it's named for, that's the model that's on there, and that's all that it is to be used for. The next question is, can I explain the meaning of the RMSE again? So RMSE is the root mean square error. The root mean square error is a calculation that is used when looking at predictive ability of models. It's basically what it's looking at is the typical standard deviation that a measurement will have. And so when I say that, what I mean is if you were to take any sort of typical scan, what would the difference between that scan and if you were to test it, you know, by the reference method, what would that look like? And so since our reference method was the dehydrator, if we were to actually go and you know, take a scan and then run the reference method by dehydrator, we would expect the standard deviation to be between that scan and the reference method to be about 0.07. Something I just remembered that I failed to kind of talk about is that since these validation data, this is all reference method specific, right? And there's all these different reference methods. The nice thing about the offset correction is that it's versatile and you can use it against any reference method that you wish. And so whatever is the typical operation at your facility, whether you're using an oven or a microwave, if you want the device to perform to the specifications of that, or, you know, to the accuracy of the microwave or the oven, all you have to do is utilize that as your reference method during these offset calibration studies. And when you do that, that's basically telling the instrument, okay, since I'm saying the microwave is the reference method, I want the instrument to perform to the microwave standards. And so all you have to do is change the offset accordingly, and it'll start reading very similar to the microwave method. Same can be said for the oven. If you decide instead that you want to use the oven, all you have to do is change your reference method, and then in turn change your offset, and then once you change your offset again, it'll be reading similarly to the oven method. So it's a really versatile tool. I just sorry, that was just a thought I had that I was going to discuss, but I totally kind of forgot to say that during the webinar. The next question is, what would you recommend for trying to scan and record the dry matter percent of a large number of fruits? So like for exporters, it's kind of hard to say an exact number. So it depends on a lot of things on your system for receiving lots or for shipping out lots. It depends on the number of fruit that you are shipping out per lot, or the number of fruit that you're shipping out in total. What I really recommend is if you want to get a little statistical with it, I would actually look up a sample size calculator. So there's these statistical tools on the internet that are called sample size calculators. And essentially all you have to do is plug in a few things like, how confident do you want to be? So if you want to be 95% confident, then you would put 95% in. You'd say, how big is your population size? So how many fruit total are there? And then it'll spit out for you a appropriate sample size that would get you to that kind of confidence level within, and so then you can kind of go off of that. I think that I don't think there is a good general kind of rule or number for a large number of fruits. I think that it really needs to be taken on a case-by-case basis. But I'd be more than happy to talk to you more about it. If you do want to email either myself or Eric, we can kind of figure it out together if you want, if you would like to kind of have an idea. The next question is, how thick must the peel be? What about other fruits like melon? Can you scan this kind of fruit? So actually the thickness of the exocarp, or the skin, or the peel, the rind, it does play a pretty critical role in how the ability of the 751 to function. As I mentioned already before, the 751 is a single commodity meter, so only the 750 can be used with multiple commodities or commodities that aren't already built into a 751. But the thickness does play a factor. So for instance, with avocado, the rind is thin enough that our lamp is able to penetrate through into the flesh. The same goes for thinner rind fruit like honeydew, for example. Actually, even though that's a little bit thicker, our instrument still is able to penetrate into the flesh, albeit not as deep into the flesh likely as it doesn't go all the way to the core or anything like that. But it is able to penetrate the flesh. Unfortunately, fruit that have really irregular or thick rinds, so things like pineapple and watermelon, those are we have not been able to be successful in getting a scan that is able to penetrate through those rinds and into the flesh of the fruit in a non-destructive way. The workaround for that is to actually peel away some of the rind itself so that you can actually get a direct measurement of the flesh. However, this renders the method from non-destructive to destructive, albeit it still is a very rapid method of testing. It does can be off-putting, I guess, to some people if they are looking for a non-destructive method. All right, the next question is, to your knowledge, have models been developed on avocado through the ripening process? And so that's a good question. Our models, currently the avocado model really only predicts well up to the around 34% dry matter range. We start to lose our accuracy once you get above 34% dry matter. So the really ripe, really mature and ripe fruit tend to not do as well. And so, but as long as your fruit, stay with under the 34% dry matter value, then our model will still predict fairly well. We are continuously working to update these models, and so we are constantly trying to increase the accuracy, increase the measurement range, all those things. And so hopefully in the near future here, we will have a new version release that will be able to more accurately measure up into the higher ranges, into the 40s, 40% dry matter range. Oh wait, I think I skipped a question. For reading, could it affect the soil or defects of the fruit? Oh, could it detect? So the question is, can it detect the soil or defects of the fruit? If you are measuring a fruit that is, covered in dirt, or one that is covered in defects, you are likely going to get changes to your readings. So we definitely always recommend, at least trying to wipe off any visible, dirt from the fruit before you scan it. And scanning directly on a defect is also not highly recommended, because those just introduce new variables that aren't really accounted for in the model. So you want to avoid scanning the defects. If you can find spots on the fruit that aren't defective, it's recommended that you scan there.
This also applies to any moisture as well, since it is a spectrometer. Any moisture on the fruit will refract, has a possibility of refracting the light that penetrates the fruit and giving you inaccurate results.
Yep. Thank you, Eric. Yeah, I totally. Yep. Yeah. So water as well. So you really kind of want to make sure that there's this minimal. It goes back to the technique thing. Is that when you perform scans, you want to eliminate as many variables as possible when you are actually performing the scans. The next question is, you talk about 2 measurements per fruit mostly. Should this be on the opposite equatorial sides? So, and that's where the fruit physiology comes into play. It's going to be different for every fruit. When you talk about 2 scans for kiwi fruit, 2 scans on the opposite equatorial sides works really well. Because the kiwi fruit is a much smaller fruit. It's more translucent than other fruits. The light penetrates really well. The rind's really thin. So that works really well for kiwi fruit. With avocado, as I mentioned, sometimes you have a fruit where the seed might be too large and actually could cause interference if you scan at the equatorial sides. In that case, you'd want to take 2 scans at different sides of the neck, or you'd want to do one at the neck and one at the base of the fruit. And so it really is dependent on the nature of the fruit itself when we do 2 measurements per fruit. But typically, though, if we're doing 2 scans on an avocado, that is what we would do. We would do, if we know that we're not going to get interference if the fruit size is appropriate, then we won't. Then we will scan both the dorsal and ventral side at the equator, and use that as our average for the fruit. Yes. All right. The next question is for the instrument variation explained slide. How much of the variation that you see when you measure fruit on the same spot? How much variation that you see when you measure fruit on the same spot on 2 instruments do you think is due to the difference in instruments versus due to measuring on a slightly different spot? I think that they both contribute. I don't know if I can put an actual kind of number to that, but definitely I think that if you're measuring a fruit on the same spot, there are some easy ways to mitigate the possibility of accidentally scanning in a slightly different spot. By tracing around the scan head, where exactly on the fruit where you're scanning, making, markings to know, making sure the fruit's in the same orientation, things like that can help make sure that you reduce that variance from measuring in a slightly different spot. However, it is inevitable that you won't put it on the exact same spot. And so that does contribute slightly to the variance. I think that, however, if you do your due diligence and you are being, as accurate as possible about getting the fruit in the same spot, then more of that variation is likely due to the fact that that those two instruments, have different offsets in them because they were calibrated with a different type of, or, different fruit from a different region, likely from a different, at a different maturity stage, different ripeness stage. So I think that that's more likely, the larger cause of variation, if you're doing your best to make sure the fruit is on the same spot and you're marking your fruit correctly. So the next question is external light influence the main cause of variation of measurements performed with the same instrument? How can it be minimized? No. So actually, we've done a lot on our end, on the engineering end, to compensate for external light influence. And we actually have a built-in reference shutter system that we utilize to compensate for the external light influence. And so that actually is not a major source of variation at all for measurements performed with the same instrument. However, that being said, you do want to make sure you do your best to cover the entirety of the lens with the fruit when you are taking scans. And so, I wouldn't, have the fruit sticking only half on the lens and you taking scans of half air and half fruit. That can influence the results, obviously, in a negative way. So just do your best to cover the lens. However, especially with fruit like kiwi fruit, for example, it's not, when you put it on the equator, it's flat, and so it's not going to sit and cover the entirety of the lens. You're going to have areas where light can get in, but that's why we have our built-in shutter system, and that is not a major source of variance. The next question is, what is a simple offset correction? So I really hope that I got some of the point across for the offset correction during the actual talk, but the offset is just basically how we calculate it is the average difference between the predicted values from the instrument and the reference method. So it's just, if you look at this table here, it's just these values, this value minus this value, which is negative 1.3. This for fruit number 2, the instrument value versus this reference method value, it's negative 3.6. So that's how we calculate our deviation. And then once you take, for all of your sample set, you take the average of all those differences, and that's your offset correction. The next question is the correction for the calibration of each instrument. So the offset correction is what we use when we initially calibrate the instruments. It's also what the user should use if they notice trends like the ones that we talked about earlier today. Each instrument has the ability to set an offset correction, and all it does is it changes the mathematics of the model prediction so that it adds or subtracts a certain value based on your study, from whatever it was initially going to predict. With this, next question is, with this offset calculation, is it possible to have a lab reference versus field measurement of the same cultivar of fruit? I imagine you're saying, so as in cultivar, as in like all Haas avocado. Yeah, so you, with the offset calculation, you can make it as specific as you want. If you are only going to be looking at one cultivar of fruit, but the model incorporates, 4 different varieties or something like that. In the case of mango, like 6 or 8 different varieties. Then if you're looking at, if you only are interested in one, say you're only interested in Kent mangoes, then it is possible to just actually run your offset study with just that cultivar of fruit. And then once you have that offset, it'll actually be specifically tailored to that cultivar of fruit, which and if you then go to try to measure a new cultivar, a different cultivar like Keat or Tommy Atkins, then we can you will likely see that the offset doesn't work as well for just that one. So if you do a calibration procedure that encompasses all of those fruit, all of the different cultivars, and then calculate your offset from that, it'll be a good device to use across all, it'll be a good general device to use across all your different cultivars. However, if you are only interested in one cultivar, then it is absolutely in your best interest to go ahead and only do an offset calibration for that cultivar so that your instrument is specifically tailored to that cultivar and to your reference method. That's what's great about the offset calculation, is that the offset correction, you can tailor it to specifically what you want. So if you want it to, your instrument to read accurately for only Haas avocado for only the microwave method, you can make sure that your offset actually allows your instrument to read to that standard. So the next question is, could you clearly indicate which areas of the avocados should be measured if you make 2 or 4 measurements per fruit? Yeah, so we typically recommend the equator. However, so with Dr. Asuna's new research coming out, we will be revising our guidelines based on what his findings are about a fruit size. So there will eventually, we will be releasing new guidelines based on fruit size. To determine where is the best place to scan, best places to scan. But for right now, for the most part, it's typically 4 locations equidistant from each other. So, 4 different locations. If you think of your equator as being a circle, so you get 90 degrees each way. You have a scan along the equator, and that'll give you a good idea. For 2 measurements, I would just do dorsal and ventral side, so 180 degrees between each measurement. The next question is it best to test the fruit on the tree when possible? It really depends on your application. If you're a grower and you want to track your harvest maturity, then I would say it is best to test the fruit on the tree. And actually, the best part about the instrument is that you can test the fruit on the tree. You don't have to pick it. You don't have to destroy it by any means. You just have to go up to the tree, go up to the fruit, and take your scan. But if you are, an importer, an exporter, or a retailer, then your application would be to test it, when it comes into your facility in lots. So it's really, it all depends on your application. But if it would be a shame to, if you were a grower, to pick your fruit and then use the 751 because it was intended to be a non-destructive device. So we don't want to have to let any of your fruit go to waste. The next question is from Dr. Asuna here. So how important is the method for getting the dry matter reference value? So actually, it's one of the most critical points of model building and validation, because you are saying that is your control, like that is your reference method. And so if you are performing that wrong, or you are doing something to invalidate those values, then you go and decide to tailor your instrument to read similarly to those values, then you've now caused the instrument to read inaccurately because you were performing the initial test inaccurately. So making sure that everything from your sampling technique to the analyst technique of actually performing the drying, your parameters for your whatever instrument you're using for drying. You know, make sure you're monitoring and you have quality instrumentation. Everything that goes into the reference method, because it is your control, it is of the utmost importance to ensure that your reference method is being performed as accurately as possible. The next question is, could you explain briefly how to correct the instruments based on the offset correction? Yes. So I don't have an instrument here with me. Unfortunately, we're working from home due to the quarantine, so I don't have an instrument physically with me. But essentially, it's just navigating a series of menus on the instrument, and then from there, you can essentially just change the number. There'll be a number input on the screen, and you can change that accordingly to whatever your offset correction is meant to be. And actually, we have really great tools to help you do this. We've created Excel workbooks that allow you to input your data, and it'll automatically calculate out any sort of offset that the new offset that you will have, and it'll also explain to you in that workbook step by step how to navigate the menus, what keystrokes to use to get to that specific menu for adjusting the offset calibration. So I'm sorry I don't have an instrument with me right now to demonstrate it, but if you have an instrument and you need to change your offset and you want to know how to do that, please send me a message, or please send me an email or Eric an email, and we will send you that workbook to help you out with doing your offset calibration. All right, the next questions are for Eric. So let's see here.
Let's see. Please, can you prepare in the future webinar about mango and another for fruit maps? Yeah, so we have presented one on mango. It is available on YouTube. I'll post the link to the mango webinar. And we do have plans for a fruit maps webinar as well that'll go over how to use the fruit maps and the functionality of it. We can do a walkthrough of how to create plots, how to upload your data from your instrument to your fruit maps account, and how you can easily export the data from fruit maps to an Excel worksheet as well. So stay on the lookout for that. We typically do a webinar once a month. And so I would expect to have this webinar or host this webinar in the next couple of months. Gloria is asking, para cualquier variedad de aguacate. So for those who don't speak Spanish, she's asking for any variety of avocado. And so our model incorporates Hass avocado as well as Shepherd varieties. We don't have, that's not to say that our meter won't work for other varieties. We just don't have any validation data to support that on our website. Hass variety is the most common variety that we have here in the States, and so we use that for our validation analysis. Yeah, and in Spanish, el modelo no utiliza, bueno, utiliza solamente Hass y Shepherd, las variedades de Hass y Shepherd. No tenemos datos de validación para cualquier otra variedad, pero eso no es por decir que no funciona con otra variedad, solamente que no tenemos validación.
Right.
You want to continue?
Yeah, thanks for that, Eric. So the next question is, hi, when doing multiple scans in single fruit, does the machine have the capability to compute the average of that fruit? So the answer to that question is yes. The machine actually does have the capability to compute the average. There is a menu. Once you have taken the measurements, there are menus that you can navigate that will group together based on your organizational structure. It'll group together groupings of measurements, and it'll show you averages of your measurements, standard deviation. And so yes, the machine does calculate that for you. The next question is, can a dual model be put in the F751? So no, the F751 is intended only for the model that we put on it for that single commodity. If you have further questions, you can always reach out to me via email if you have a specific need that we can help you navigate.
I think Brenda might also be asking if it's a dual characteristic model can be
okay.
incorporated into
That's
some
why
framework.
we're both on this, so that you can help my mind think clearly when I'm when I'm obviously thinking of a totally different response. So yeah, so the kiwi fruit meter has Brix and dry matter built into it, as well as the mango. The mango also does Brix and dry matter. The avocado, we stuck with only dry matter because that is the most commonly used harvest maturity indicator and quality indicator because it correlates really highly with oil content. But when we build models, when we first kind of conceptualize it, we do our research to see which parameters or indicators are most important to that industry, and so then we pursue those to actually be built into the model. So yes, so for that, and if that was the intent, then yeah, that it is possible.
Gloria is asking, los agricultores necesitan recolectar la normativa cuando los aguacates, por ejemplo, hojas, tienen 21% de materia seca. Un error de 2% puede hacer que no cumplan la normativa. ¿Se puede solucionar de alguna forma? Si quieres, me puedes mandar un mensaje por correo y, bueno, por ejemplo, el equipo siempre va a tener un porcentaje de error. También, al igual, un método tradicional. Eso siempre va a ser un problema. Entonces, sí puedes reducir el error, pero para eliminarlo nunca va a ser posible. Pero podemos hablar más sobre este tema si me quieres mandar un mensaje por correo, y claro que sí, hablamos más sobre esto. Gloria is asking, so at the moment of harvest, Haas needs to have a 21% minimum dry matter percentage. An error of 2% can make it where the lot fails. So is there a way to fix this, correct this? And I was mentioning that our instrument is always going to have an inherent error, and just the same way as any traditional method has one as well. There's ways to minimize the percent error and in sampling, but to eliminate all error is not possible. So again, consistency is key to any way that you test your avocados, and to reduce the error percentage, but to eliminate all error is not possible.
All right, thanks, Eric. The next question is, can this machine work with table grape or wine grape? So again, these F751s are single commodity meters. This F750 is our research unit, which can be used for commodities that we have not built models for yet. It does require the user to build their own models, but we do not currently have a table grape or wine grape model built. We have shown that it is possible to use the 750 for table grapes. We have application notes on our website. I would encourage you to check that out. The next question is, could you explain the relationship between dry matter and oil content? So actually there is a really good resource that you should check out. It is UC Davis has the Post-Harvest Research Center has a thing called Produce Facts. And that is a great resource to look into. But essentially, it's not a one-to-one relationship or anything like that. But it is essentially that higher dry matter is equal to higher oil content because there's less water. Oil content is technically part of the dry matter measurement because it is not water. And so higher dry matter, higher oil content, higher desirability or quality. So that's that relationship. The next question is to determine the dry matter content by destructive methods, how many samples do you recommend per fruit? So for doing it by destructive methods, I would actually say that what's best if you want to get an idea for the whole fruit is to get a representative sampling of all the flesh. And so there's multiple ways to do that. Some people use slices from the avocado. Some people, take core samples. What I would recommend if you want to, do cores, then you would want to take multiple cores from multiple locations in the fruit, probably, at least 4 locations. But however, I think that if you want the best whole fruit average, the ideal way is to sample all of the flesh, or at least, a majority of it. I know that some people also use a minimum of like 5 grams of flesh, and that's a good way to make sure that you're utilizing as much as you can without causing the experiment to take forever, and so that's a good compromise. But I would say there isn't an exact number, but I would say that it wouldn't be appropriate to only use a gram of the flesh or 1 or 2 core samples, depending on how big the core samples are, I suppose. But you want to at least get a good representative sample. So if you were to open up that avocado and look at it, you would want to look at it after you have sampled it. You want to look at it and be able to say, yeah, that looks like it would represent what the entirety of the fruit flesh would be. So, multiple locations, so more than 2 locations, and ideally, more than a very small amount of flesh. You want flesh that ranges all the way from the seed all the way to the outside, to the rind. So that's what I would say to that. The next question I've already answered. It's how to calculate the prediction correction intercept. We're still on the same page. So it's just the average of the differences between the instrument prediction and the reference method. And the next question is, can a significant amount of error be caused by variations in skin thickness within a commodity? Working with apples, and I'm wondering how the measurements will vary between cultivars. So actually, thickness only really plays a role if it's going to impede the ability of the lamp to penetrate into the flesh. Obviously, but there are no apples that I can think of that have a thick skin thick enough that would cause any sort of extreme variation. We are currently working on an apple model that is going to incorporate many cultivars. Actually, if you want to just talk about it more, I would recommend getting in touch with Eric. He's kind of heading that project. Eric, if you have more to say to that, you can feel free to jump in. But that's from what I understand, I can't see a way that any variations in the skin thickness of an apple would really cause any issues for our instrument.
Yeah, I don't anticipate variations in skin causing an issue. If the model is multiple varieties, different cultivars, then that variation should be built into the model when the spectra is collected. So I think I don't anticipate that being an issue.
Yeah. All right. The next question is, do you do the correction for each device batch yourselves, or does the customer need to do it according to his or her reference? So that's what I was talking about earlier when I was talking about our current method. We do perform a calibration for the offset prior to shipping out. We do it in-house. Right now, we do it with the fruit, on a batch-to-batch basis. We buy fruit from our local markets, but we are currently changing that method to a method where we will reduce or ideally eliminate the variation between production batches. However, there are cases when just differences in region or cultivar or whatever do cause the need for the customer to perform their own offset calibration. And so that's why we presented this data to you today, to show you that it is a powerful tool. If you notice your instrument, if you want your instrument to behave exactly to your current methods and with exactly your fruit, then it is in your best interest to perform one of these offset calibrations. The next question is, does the model introduced in the instrument been performed with a dry matter methodology in which water is completely eliminated? From my experience, 24 hours in an oven is not enough time because of the high oil content of avocado. Yes, so 24 hours is actually not typically what we usually go 48 hours, 2 days for ours. I think I might have said 24 hours earlier, but I was thinking of kiwi fruit in my mind while talking about avocados, likely. When we did a lot of the model, the actual data in the model was collected by our friends and collaborators in Mexico and Australia, and then California as well. So for the most part, and they are trusted researchers, scientists themselves, and their methodologies we are confident in. We're able to fully eliminate water. However, that's kind of a little bit of a false statement, because you'll likely never truly eliminate all water, but that's kind of a subtle, not subtlety, but I'm just kind of nitpicking there. But yeah, our data that's in the model is with, and as well as our validation, we do make sure that our methodologies, our destructive methodologies, are working correctly, and working efficiently and working accurately. So I think I might have skipped a question on you there, Eric.
Yeah, posted at the top for some reason. They can go ahead and send me an email, and I'll go ahead and help them with the support question. There's a support question.
Okay. If you guys have any specific questions about your instruments or support related things, please reach out to our support team, make a ticket on our website. We'll get to you on that. Um, and then this next question is an offset correction enough for temperature effects? So our model does compensate internally for, we did build in some temperature compensation. The reason I mentioned the heating up of the fruit is that our model compensates for temperature to the degree of what varying working conditions, but the lamp can heat that fruit up to even higher temperatures than what typical field or storage conditions might be. So the offset correction doesn't need to be done for temperature effects for the avocado. We're also currently working on updating our kiwi fruit model to allow for temperature correction as well. But if you are noticing, if you work in an exceptionally cold environment or something like that, it may be that a temperature or offset correction can help with any sort of effects you might be seeing from that temperature. Like I said, this offset correction, it can be tailored to your exact working environment and your technology, your fruit, your environment. For different types of avocado, for example, Fuerte, could the F751 be recalibrated? So we do anticipate that. We don't have any data to support that claim yet, but we do anticipate that an offset correction could be used in order to use the 751 avocado model on other types of like tropical varieties or things of that nature. So we are optimistic and are hopeful about that possibility. I don't have any data to support that claim though. The next question is following up from the question if it is best to measure on the tree. Do you expect the spectra to be different if you measure on the tree versus right after picking the fruit? So I don't anticipate there being that much of a difference. The only differences that would arise are those that would arise depending on how long of a time span that is between being on the tree or being picked. So if you were measuring on the tree and then you picked the fruit and then you waited, especially a long time, like a day or a couple hours, then there likely might still be a difference because the fruit is still physiologically changing. If you're asking that if you were to measure the fruit on the tree or pick it and then measure it at the same time point, there might be very, very small differences, but likely not too much of a difference there. All right, the next question is, which method for dry matter is used by the company to create the reference values? Depends on the fruit. So with avocado, we are currently using the dehydrator. We were previously using the microwave method. However, we noticed some bias with the microwave method, the automatic microwave system that we had. Its ability to dry without burning was fairly limited. Its power settings were just a little bit too high, and so we switched back to the dehydrator method. And then for kiwi fruit, it's also a dehydrator. And then I think mango, actually, we also use the dehydrator now because the kiwi and mango both are pretty susceptible to burning. So you can't really use the microwave. However, so that's what we do right now. That's something that's going to be completely changed here soon. We're looking into new ways to perform this calibration to increase the consistency between batches and reduce that variation between production batches. The next question is, what is Fruit Maps? Fruit Maps is an application that is used alongside the 751. It's used for harvest tracking. We are currently making updates to it, and that's what Eric was talking about earlier with one of the questions. So we do have more information on it on our website if you want to check it out. It's basically just an app that you upload your 751 data to, and it will allow you to track your harvest more efficiently. The next question is, what instrument will you suggest for a determination of maturity in plum and peaches? I would recommend the 750. However, we do not have a model built for plum and peaches, so you would have to build that model yourself prior to being able to use it in a non-destructive way. The next question is, if I want to scan Haas, thick skin and a thinner skin avocado, can I use two different models in one device for avocado? So you're saying that you want essentially you want a model that is specific to a cultivar. You want a thin skin avocado model and a Haas model. So ideally, if there, what we are hoping to have is a singular model that can predict all of them, regardless of skin thickness. And we're hoping that with the addition of more data into our model, that there will be no need for the two different models in one device. But if you want to talk about it further, we can discuss it more over email if you want to email Eric or myself. The next question is, what about variations in avocado skin thickness? Yeah, going back to that, that also shouldn't play too much of a factor in the instrument's ability to read. The one thing is that a thinner skin does allow better penetration of the light, which could be good. It could be bad if your seed is really large and your skin is really thin, then you can run the risk of accidentally, getting variance from the light hitting the seed. It really the skin thickness shouldn't influence the model's ability to predict. However, it will, just due to the fact that there are some other possibilities like that seed situation. Also reducing the amount of ridges for like smooth skin avocados. That actually makes it easier for the instrument. It reduces variation. So really, truly, Haas is one of the more difficult, fruits to utilize this instrument with. But we've by creating this robust model, we've managed to overcome a lot of that variation that's caused by the fruit itself, and the user can overcome a lot of it just with the technique involved with performing the scans. So I think with that being said, there are, we don't have any data to support other varieties that aren't built into the model. However, we hope to soon have some good data on that. We do have collaborators currently working on projects looking at other cultivars of avocados. So, and I think that's the last question. For all of you that are still on, I applaud you. Thank you for sticking with us through all those questions. If you have a question that is more specific to your situation, you can always book a consultation with us or email Eric or myself directly. And yeah, that's it for today. Thank you guys all for joining us. I really appreciate it. And if you need a quote for an instrument, go ahead and click the link for the quote or contact our sales department. If you need help, if you already own one, or if you need help with an application, talk to Eric or myself via email or book a consultation at the link below, and we'll get back to you. So thanks again for taking your time out of your busy day to join us. I see we still have 45 people on, so I really appreciate it. This will be recorded and sent out to you, as Eric mentioned, and we also will have the PowerPoint posted as well. So thank you all again. And Eric, do you have any closing remarks too?
No, just again, if you have any email questions, I shared both of our emails in the chat box. Bridget, I wanted to mention that I'll send you the email about dry matter and oil content relationship, and that's it.
All right. Well, thanks again, everybody, and I hope you are all staying safe and healthy. And I hope that for you in the produce industry, that things continue to go well with the produce industry, and that you know, continue to stay busy without going too crazy. So thanks again, everyone, and have a great day.